In this video, I'm going to do my best to explain wave equation. And wave equation as a whole is very similar to heat equation because you have your four steps. You have separation of variables, solving an x-ODE, which is just finding eigenvalues and an eigenfunction, solving a t-ODE, and then using Fourier series to find some unknown coefficients and then put our answer together. But wave equation is just overall longer, but I will go through every step and try to explain everything and why we do every step. So first, we have all this information that doesn't mean anything to us right now. So first we have this equation with some partial derivatives of u, and similar to heat equation, our u is equal to capital X of little x times capital T of little t. And then our bounds for this are 0 is less than or equal, or x is greater than 0 and less than pi. So we can treat pi as our L in case that makes it easier. So this equation with our partial derivatives is our partial differential equation, or PDE. And in wave equation, we're usually going to have this a squared, and we're also going to have a double partial view with respect to t. And this is the sole reason why wave equations are so much longer. I'll explain later, but it basically makes it so we need to do double the work when we find our coefficients. And next we have our boundary conditions, which are noted by when x is 0 and L, with L being pi in this case. And what these mean, so in a wave equation, we have some string in some place. And we're looking at two ends of the string, the left and the right end. And so when x is 0, it refers to the left end, and basically where it is in our plane. So when x is 0, the wording they like to use is that it is secured to the x-axis. And then when x is L, or in this case it's pi, we look at the right end. And in this case, because it's 0, even though my drawing doesn't really show it, there we go, our right end is also secured to the x-axis. These may not always be 0. It could be a function, and if it's a word problem, it could say like the right end is moving in a manner related to a sine function. They'll give you the sine function. And for both of these, t is greater than 0. And that's what our boundary conditions mean. And then we have our initial condition. Our initial conditions, we have two, unlike heat equation. So we have one when, both of them are when t is 0. But one is our first one here, u of x0, that represents our initial displacement function. And then this partial view with respect to t, it's just a fancy way of writing ut x, and then they give us t is 0. And this represents our initial velocity. Usually, in the problems I've seen, one of these is usually 0. So you're not going to have to, so that means one of our coefficients will be 0, and it's a lot less work. And I think that's pretty much, that goes over the info they gave us. And so how to use this information. All this is going to correspond to a step of the question. So our PDE is used for separation of variables. Our boundary conditions are used to solve our x-ODE. And then our initial conditions are used for finding Fourier coefficients. So first, we'll start with separation of variables. We have a squared double partial of u with respect to x is equal to the double partial of u with respect to t. So going off of the fact that u is equal to x times t, we can use stuff we learned in MA221 with partial derivatives, where we treat so in this case we're dealing with x, so any other terms are treated as constants. which leaves us with x double prime little x times capital T of little t. And then similarly for the right side, double partial of u with respect to t. Sorry for the bad handwriting. Is just capital X of little x times t double prime lowercase t. Now what we can do is we're gonna plug this into our equation. So we have a squared x double prime t equals x times t double prime. I'm not gonna write out like this parentheses stuff right now because it just makes it longer and doesn't add anything. So now we need to separate our variables. We need to get all the x's together and all the t's together. But we also have this a squared. So where does this go? So just like heat equation, any constant needs to go with our t equation. So we can divide them out. And that leaves us with x double prime for x. And these are all capital X's, no lowercase x. It's equal to t prime, or t double prime over a squared times t. And then we set both of them equal to negative lambda. And so now we have two equations, and now we have to write each out. So we'll start with the x one. So x double prime over x equals negative lambda. We have to get this in the standard form. So we need everything to be on one side or on the same side, and we need the x double prime to be isolated. So we can multiply both sides by capital X to get x double prime is equal to negative lambda x. And then we bring that over to the other side, and then we get x double prime plus lambda x equals to 0. This is our XODE. Now we have to do our TODE, which is the same process. We want to isolate the t double prime. So we can multiply both sides by a squared times t. So we get t double prime minus lambda a squared t. Bring everything on the same side. And you have t double prime plus lambda a squared t equals 0. And this is our TOD. Then I'll just move this up so you have some space. Okay, that's step 1, separation of variables. Next, we have solving our XOD. This is just an eigenvalue problem in disguise. That's kind of the trend with these questions. They have a bunch of concepts we already learned, but they disguise it as a very hard question and a long question. So we got to solve this ODE here. And this is where we use our boundary conditions. But the problem is our boundary conditions are for u of xt. And our equation here only has functions of x. So what we do is we take our equations and we plug them into u of xt, which is this again. So our first one, we look at our left end of our string. So it's x of 0 times t of t equals 0. So in order for this to be true, one of these has to be 0. But we know that t is greater than 0. So therefore we assume that t of t is not 0, which means that x of 0 is 0. It's our first condition. Then we have u of lt, which is pi. Our L is pi in this case. That's also 0. So we do x of pi times t of t equals 0. T of t can't be 0, therefore x of pi is also 0. Now let's just group everything we have. So we have our ODE we're trying to solve. And now we have some conditions. And now this has become an eigenvalue problem. We have everything we need to solve it. So imagine you're solving an auxiliary equation. We just need to state that we're using e to the mx. This is the thing they want you to do. And if we were to try and find m, m is plus or minus negative lambda. Now, my TA told us that we're only going to need to consider two eigenvalue cases, with one being lambda 0, which is repeated real roots, and then case 3, which is lambda is greater than 0, which is complex roots. So first I'll do case 1, lambda is equal to 0, which is also repeated real. So what happens is both of our m values become 0. So we write our equation. We have c1, and what happens is because it's e to the mx, so it becomes e to the 0, which just becomes 1. But because this is a repeated root, our other constant's multiplied by x because you can't have the same m value. So now we could plug in our stuff from up here. So we'll do x of 0 first. We get c1 plus c2 times 0 is 0. This cancels out, and we're left with c1 equal to 0. And then we can do x of pi, c1 plus pi c2 equals to 0. We already know that c1 is 0, so we're left with pi c2 is equal to 0. Pi is not 0, so therefore c2 has to be 0. And in the event where they don't give you pi and they give you L, just know that because L it basically represents like the length of the string, your L can never be 0. So we have C1 and C2 are the same, they're both 0, which makes this trivial. And we have a trivial solution, and we have no eigenvalues here. And that's the only reason why we do case 1, just to prove that there's nothing, that case 3 is the only place we get eigenvalues from. If we were to do case 2, which is distinct real roots, you'd also get a trivial solution. So now case 3, which is lambda is greater than 0, complex roots. So with complex, we have m is equal to plus or minus I of square root of lambda, because we have a negative in the square root, which is not allowed. Sometimes they like to set this equation equal to like alpha or alpha squared and solve it like that. It doesn't change anything. It confuses me, so I'm not going to do it. I find it easier this way, and you have to do less backtracking later. And so when we do our complex roots, we get it in the form of c1 times cosine x, and then our m value, which is square root of lambda, and then we have plus c2 sine, and then the same thing inside. So now we have that, and just like with case 1, we can plug in our conditions, our boundary conditions. So x of 0, when we plug 0 into cosine, it becomes 1. When we plug into sine, the whole thing becomes 0, and x of 0 is 0, so c1 is 0. And then for x pi, we already know that c1 is 0, so we can just consider c2, and it becomes c2 sine of pi lambda squared, or square root of lambda. So the problem is that we can't have a trivial solution again. We already had it in case 1 and 2 if you were to do case 2, and we need to get eigenvalues. So what we know about sine is that sine of n pi for all integers n is equal to 0. So we need to find an eigenvalue that makes this 0. That makes the sine function 0. So what we do is we can take the inside of the sine function and just set it equal to n pi. We divide out the pi, which then leaves us with square root of lambda equals n. Then we have to remove the square root, so we square both sides. And then lambda n is n squared. That's our eigenvalue, but we still need an eigenfunction of x. So we represent that as xn, and we go back to our original x equation. And we already know that c1 is 0, so we're only looking at the part with sine. And you're plugging in lambda into the square root, so it just becomes sine of nx. And that's our function. Let me just make sure I'm doing all this right, because it would suck to backtrack. Okay, everything is good. And then n is just 1, 2, and all integers after that. So that was step 2. Now step 3. This is where things start to differ from our heat equation, and this is why everything is longer for this. So our TODE is T double prime plus lambda a squared T, or big T, my bad, equals 0. Now, unlike our heat equation, our wave equation has a T double prime, which means we have to solve it in a similar way to the way we solved our XODE. But this time we don't need to do cases. We don't have to do case 1 and all this stuff because we don't have conditions for that. So we can basically treat it as a case 3 eigenvalue question, where m is plus or minus square root of, would be negative lambda a squared, which just becomes plus or minus I a square root lambda. And so when we plug it into our case 3 function, I keep saying case 3, but we're just getting it in that form. We're not actually solving for eigenvalues because we already did that. So what happens is it becomes C1 cosine A square root lambda plus C2 sine A square root lambda. And so, but now and we're not done with this yet because we still have a lambda in here, and that's not good. But we already found lambda, so we can just plug it in. Tn, and I'm also going to change these constants to capital AN and then capital BN. So we plug in our eigenvalue with AN. I forgot the T. Made a big mistake. So here so when we did our XOD, we had an X inside, but here we're gonna have a T because our function's with respect to T. You rewrite that. And so when we plug in our eigenvalue, we have cosine of A and T, or cosine of ant, plus, and we're changing the C2 to a BN sine of ant. So if you see ant, you're doing it right. And this is step 3, or TODE. And so step 4. So the first 3 steps were basically getting pieces of our final answer because we use the equation to get 2 ODEs. Then we solve those ODEs so we can get an eigenvalue and then 2 functions. And now it's time for the 4-year stuff and plugging everything in. So we already know that u of xt is x, capital X of lowercase x times capital T lowercase t. But we found functions that rely on n. And anytime we have n, where n is a number from 1 and it increases every integer afterwards, that means we have a Fourier series, which we all love doing. So it would be like this, xn, tn, their series. And so we can plug in the values we got. And luckily our x function is very nice. And our t function is not so nice. So now I have this, but we have two unknowns. We have these are Fourier coefficients, and we need to figure out what they are. So if we look at what a Fourier series looks like, you can see how we have like an a naught, and then in our series we have a lowercase an with a cosine, and then lowercase bn, and then a sine. Our function's not in that form right now because we have this extra sine of nx on the outside. So to fix that, we look at our initial conditions. So we have two. We'll go over the first one, which is u of x 0 is equal to a little sine function. So u of x 0. And what we do is anytime we see a t, we just plug in 0. Equals 1. The sine of nx stays the same. When you plug in 0 into the cosine, it goes to 1. So an. When you plug it into sine, it becomes 0. So now we have it in a very familiar form of a sine series. And that's equal to our initial condition, which is 0.01 sine of 3 pi x, and are bound from 0 to pi. So let's look at what a sine series is. Our sine series is basically like we're treating capital AN as lowercase bn because the type of series is mainly dependent on whatever our x ODE resulted in. So that's why we're going to do a sine series here. But the thing with Fourier series is that it applies to bounds of negative L to L. So in the context of this problem where we know that L is pi, the bounds would have to be negative pi to pi, which isn't what we have. We have 0 to pi. So we have half the range, which makes us a half range Fourier expansion. And what happens for a sine series, it's very similar to a regular Fourier series, but you have this, instead of 1 over L, you have 2 over L. And that just happens because we have half the range. So you do 1 over L over 2, and then when you simplify it, it just becomes 2 over L. So let me write that out. And our f of x in this case is this sine function thing. So we say capital AN, we can just treat it as a lowercase bn in a Fourier series. 2 over L, which is just pi. And then our integral is from 0 to pi. Our f of x. And because we could actually pull out the 0.01. Actually, let's just make it even simpler. We'll make it this becomes just 1 over 100. put that in. And then we have sine of 3 pi x times, we have to consider the sine nx dx. So by finding this integral, we can figure out our first coefficient. But we have a product of two sine functions. So how can we have to figure out a way to solve this integral because we can't use integration by parts in this current form because it would probably go on forever. But luckily we actually have a trig identity that lets us solve this. So we have, I'm not going to focus on the cosine one, on the sine one, where the product of two sine functions is equal to 1/2, and then in parentheses you have your cosine alpha minus beta minus cosine of alpha plus beta. So in this case, we have alpha is 3 pi x, beta is nx. So let's rewrite this as 2 over 100 pi integral 0 to pi 1/2 times, I'm just going to go back and forth, cosine of 3 pi x minus nx, and it's another minus and a plus, minus cosine 3 pi x plus nx. So now we have an integral that we can solve much easier. So what we do, I'm going to rewrite this again, so we can pull the 1/2 out, so we're left with 1 over 100 pi. And then now, because we're taking the difference, it's the integral of the difference of two functions, we can split this up into two integrals just to make this a little easier. So we have cosine of n pi x minus nx dx minus integral of from 0 to pi cosine 3 pi x plus nx dx. So now I have two integrals that we can solve using u substitution, or we can just, similar to the way I did it for the heat equation, we can just take the integral of the trig function and divide it by, or we can multiply by the reciprocal of the non-x terms inside. So I'll just write it out because that probably makes more sense. So 3 pi x minus nx divided by 3 pi minus n from pi to 0 to pi. So if you were to take the derivative of this fraction, if you were to take the derivative, you would find that it would just equal the same cosine function from before. And then now we do the other equation. So then minus, put that in parentheses to make it a little more legible. So our numerators very similar, we just have plus nx instead of minus nx. And then this time our denominator is 3 pi plus n from 0 to pi. And I'm kind of running out of space, so I'll just bring this to the next page. So now we just have to plug in our bounds. So 100, or 1 over 100 pi. So when we plug in this, just making sure everything is right. Yes. We're left with sine of 3 pi squared yeah, 3 pi squared minus n pi. If you want, you could, within this sine function, you could just factor out the pi, but I'm just gonna leave it like that because it's easier. With this, when you plug in 0, the whole thing is 0. And then for other integral, pretty much very, very similar overall. And then that should be, oh, I used the wrong identity. This is supposed to be a plus, I believe. Yeah, that thing was wrong. I'll fix that later, but the identity adds them, at least according to what my TA says, and I trust her more than some random picture online. So then this is our first coefficient, capital AN. But now we have to find BN. I'm not going to plug in AN yet because it just makes it harder to read and it doesn't help us at all. So we have to look at our second condition. Our second condition is the partial view with respect to t, or our initial velocity, is 0. So to figure that out, let's backtrack to this great series we found earlier. That. And then, so what it says is it says that partial view with respect to t at t equals 0 is 0. Or we can write it like this. And so that means we have to take the partial derivative with respect to t for this whole function, or this whole series in this case. Yeah. So when we do that, I'm not going to plug in t just yet. I'm going to do our derivative first. So this first sine function doesn't have a t at all, so it remains constant. And then when we do this very big derivative, we're left with our negative an times an times sine of ant plus bn times an times cosine of ant. And we're left with this huge function. And then, of course, we set that equal 0 because that's what our condition says. I don't know if I wrote it up here. No, I did. Never mind. So now we can plug in t equals 0. And when we do that, sine of nx remains the same. So this is probably going to be another sine series. When we plug it into sine, that whole term goes to 0. And then we're left with bn times an. And then the cosine just becomes, cosine of 0 is 1. So now we have another familiar series. We have a half-range sine series, which means that we can treat this capital Bn as the lowercase bn, which is just like from a coefficient from a regular Fourier series. 2 over pi again. Integral from 0 to pi. And then, in this case, our initial condition is our f of x is just 0. Sine of nx dx. And this integral, because it's just 0, becomes 0. So we have two. Now we have our two coefficients. So bn equal to 0. Highlight that. And then I'll highlight this as well. So now, oh, and one more thing I forgot to mention. Because we have this an here, these constants, when we're considering bn, it's not only, at least this is what my TA says. Yeah. The capital BN times AN is 0. That doesn't really change anything, it's just like a definition. I doubt they'd really take points off for that. So now we have both Fourier coefficients, which means now we can go back to our original u of xt, and we can plug them in. So we have the infinite sum, n equals 1, sine of nx, and then now I'm just going to copy and paste it. I'll erase all that highlighter stuff. And what happens when we plug in bn? Oh, wait, one more thing. This is multiplied by, so when we go up here, we see that an is multiplied by the cosine ant. So we can't forget that. And then that's plus bn times sine ant. You probably wouldn't need to write that because it's just 0, but I'm going to write everything. And that then means this whole thing is our final answer. So with this question, this would be your answer for solving the wave equation. So very similar to heat equation, but because our t function has two coefficients, we have to find two coefficients in step 4, and because we're usually plugging in t as 0, one of the coefficients gets canceled out in the first step, so that's why we need to take the derivative. So then the trig functions sine becomes cosine, cosine becomes sine, and that lets us find the other coefficient. And usually one of them is 0. Otherwise, this question would be a lot more work. But yeah. So now I have one more question. It's very similar to this one, except this time, let me go to a new page. So this is the exact same question, except our initial displacement, the u of x0, is 0, and our initial velocity, which is the partial v with respect to t, is sine x. So first what I'm going to do is just take, there's no need to redo the whole question, because it is literally the same thing, same bounds, just different initial condition, which means only step 4 changes. Erase that. Okay, so now let's find, so we got to find a new set of Fourier coefficients for this question. So we plug in u of x 0, t is 0. We get a series sine nx times an equals 0. When you solve for an, we know that this is a half-range sine series. So we do, well, not 2 over L, 2 over pi, yeah. From 0 to pi, but because this condition is 0, whole thing is 0, so this time an is 0. So now we need to find bn. And this is where we take that derivative we found before. So we can reuse most of this. So this is the same derivative from before, same question still. So what happens now, except our equation is equal to sine x. And this question I got, this is from one of the WebAssigns. It's WebAssign 12, the last question. And this question is similar to the last heat equation question I did in the other video, where our answer isn't going to be in the form of a series. It's going to be just like a function with n values we already plugged in. So before I do this integral, or actually I'll write out the integral. Sine of nx times sine of x. So we learned from last time that when you have the product of two trig functions, you can use an identity to make it into something that you can integrate. But this question doesn't want the answer in a series. It wants you to plug in n values. So what we're going to do is we're going to find some value of n that makes the sign in our series equal to the sign from our initial condition, which in this case is just n equals 1. But unlike the heat equation question, we're not done, because we also have to consider this an here. So what happens, so we assume we're making n equals to 1, which means that we're really trying to find, instead of bn, b1, because n is 1. So so what happens is we plug in n, and then we have, actually, let me write out the whole thing. No. Plug in 1, it becomes sine of x times sine of x, so sine squared. And then, but we also have to consider the an, so we have this a, which we can pull out. And because this a exists, we have to do this integral because we need to know our coefficient is unknown. It's not going to be 1 so we have, imagine there's like a 1 here. That's not, if this were a heat equation, we wouldn't need to do this integral, but because that constant a is there, we do have to do it, which only happens when you're taking the derivative. So luckily there's an identity that makes this integral possible. So first, just rewrite that. The identity states, I believe, and I think this one is right. Yeah. Where sine squared x is the same as 1 minus cosine of 2x over 2. And now this integral we can solve. So we can split it up into two integrals, and we can also pull out the 1/2. which leads us to just a over pi times integral 0 to pi of just 1 dx minus same integral, but for cosine dx. So just solving this integral the same way as we did the others. It's all very repetitive. They can, of course, give us, you could sometimes have to do integration by parts, depends on the function they give you, but it's just the same, it's pretty much the same every time. Like you just split it up where you can to make it easier. Or if you want to do one big integral, that's up to you, but I wouldn't. So we have x from 0 to pi minus, put this in parentheses. No, we don't need parentheses. No, we do need parentheses. Sine 2x over 2, 0 to pi. And now we just plug in our conditions, or bounds rather. So it becomes pi minus 0, that's 0, minus, so we have sine of 2 pi over 2. I'll leave these in here. Sine of 0 over 2. This is 0. And sine of 2 pi is also 0, because if you consider that, remember that sine n pi, where n is an integer, always makes it 0. So what happens? So this also cancels out. And then we're just left with, and then we have a over pi times pi, which is just, wait, no, I messed up somewhere. Where did I mess up? Let me see. I know I did this earlier. Oh, very silly mistake. So what happens is that this an, we consider, like we did up here, where we considered bn times an as our whole coefficient. We have to divide out the, what happens is it becomes b1 times an, or 8, and a is 1, n is 1, so it just kind of vanishes. And then we divide out the a to isolate b1, and then we're left with 2 over a pi. And that makes all of this 1 over a pi. And that leaves us with our coefficient as 1 over a. So we have a coefficient now, but we also plugged in a value of n, which means our answer isn't going to be a series. Our answer will be u of xt, xn, tn, for all n we have. So for this, it'll be x1, t1. And then when we do that, this should evaluate. So we have our sine of x, which is our x1, times our t1, which just becomes, I'll write out the whole thing. So we know that, so we plugged in a1 cosine, so normally it'd be ant, but we know that n is 1, plus bn, or b1 sine of at. Now, we actually never found a1, but we did find an, and our an was 0, so if an is 0, regardless of what value of n you have, that coefficient is always 0. So, I was right, this is t1. So when we plug in our coefficients, the sine x stays. Because we know that an is 0, a1 is also 0, that cancels out. And then that's multiplied by b1, which is 1 over a, times sine of at. And that's the answer to this question. So that's pretty much it for wave equation. Just a longer form of heat equation. And yeah, you could have, your answer could be in terms of like this series, or if you choose to plug in a value of n to make it easier, it could be like this answer where we plugged in n, so we don't need to have a series, and we did that just to make it easier. So like in this question we didn't even need to substitute a value of n, because we would have only had two integrals if we did it with the trig identity I showed in the heat equation video. But the web assign wanted it in the way we solved for it, and there's always a chance they ask it on the test. I don't think, I'd hope they wouldn't give us a wave equation, just because it's a lot more work. But I'd say if you can do a wave equation from scratch like we did, you'll definitely be set for that part of the test. I posted, my TA gave us really detailed solutions for wave equation and like other stuff. So I posted that in a Google Drive. I also uploaded an email of the exam breakdown she gave us, and I also put some other stuff, and I'll probably put this file too in there. And if you have Marissa as your TA, you already have most of the stuff in there anyways. So huge thanks to her, otherwise I wouldn't understand any of this. So hope this helped. If there's anything wrong or any mistakes I made, just please let me know.